Hello everyone, I'm Yunkai, a PhD student at Nankai University. I'm going to give you a presentation. The topic is password guessing using random forest. This is the joint work of our collaboration with Peking University. Passwords are ubiquitous in our daily digital lives, and password-based authentication will remain the most widely used authentication method in the foreseeable future. However, billions of passwords have been leaked, particularly poorly picked and protected passwords continue to be one of the major sources of breaches. For example, in June 2021, hackers utilized leaked passwords to breach the network of Colonial Pipeline. In September 2014, a bug in Find My iPhone allowed attackers to guess weak passwords and leak celebrity photos. In September 2015, hackers exploited leaked passwords to gain unauthorized access to the department's system and obtain the fingerprint data of 5.6 million users. In practice, guess number is found to be a good metric to evaluate password strength. Those easily guessed by an attacker are considered weak passwords. Thus, it's imperative to study password strength from the attacker's perspective. How much security strength can passwords actually provide? It relates to a more fundamental question: how to guess the user's password with the least number of guesses. Before starting, I will introduce the two most typical guessing scenarios. The first is the trawling guessing scenario. In this scenario, the attacker generates the same password guessing dictionary for all attack targets. The second is the targeted guessing scenario. In this scenario, the attacker generates a corresponding attack dictionary for each target user. Here, the label on the right represents the personal information of the target user. For example, B sub-0 represents the birthday of the target user. Next, let's discuss the research advance on password guessing. In general, password guessing can be categorized into two technical approaches: statistical-based and deep learning-based guessing methods. Despite numerous similar studies, we found that there are no password guessing methods based on classical machine learning techniques. Now, I summarize the existing password guessing methods. It seems that classical machine learning techniques may have a performance somewhere between deep learning and statistical methods, but there's a lack of relevant research. To address this gap, we have raised the following questions. Can classical machine learning techniques be used to design password models? If it's possible, how can these techniques be applied to typical guessing scenarios? Can password models based on classical machine learning techniques improve the guessing success rate? Although applying classical machine learning techniques to password guessing may seem simple, it's actually quite challenging. First, passwords are essentially short texts and have some characteristics that differ significantly from traditional NLP tasks. Second, cracking passwords requires an exact match, that is, any vagueness will not succeed. Additionally, determining how to construct password features to ensure the effectiveness of machine learning algorithm is not straightforward. Next, I will explain in detail how classical machine learning techniques can be applied to password guessing. We first model the password guessing task as a classification problem. It should be noted that our work makes the same assumption as the well-known Markov model. Each character in the password is only related to the previous characters. Based on this assumption, we can perform password guessing tasks. Here we provide a toy example. In this figure, PASSWO is the sixth-order string to be classified, and we use a classification model to predict the correct label. A key issue here is how to construct password character features. We mainly consider four types of password features. Specifically, each character is represented by a four-dimensional feature vector. The entire n-order string uses 2 dimensions to represent the current length feature. For example, the character W in the 6th-order string WER654 is represented by the vector 3, 23, 2, and 2, where 3 represents W is a lowercase letter, 23 represents that W ranks 23rd among A to Z, 2 represents that W is at row 2 of the keyboard, and the last 2 represents that W is at column 2 of the keyboard. The last feature 7.3 means that the last character 4 in this 6th-order string is located in the 7th position of the entire password, and the character 4 is located in the 3rd position of the number segment. Considering that when the data dimension is low and the task accuracy required is high, ensemble learning method generally performs well. In what follows, we take random forest as a typical case study. The decision tree is the basic unit of the random forest. Here is a high-level example of a decision tree for password prefix classification. The node division is determined through if-else logic based on corresponding rules, and each prefix is ultimately divided into the character category. Then we vote on character classification results with the random forest. The remaining password generation process is the same as the Markov model. Next, let's move on to the experimental setup. We have used 13 password data sets. We set up both large-scale and small-scale training scenarios, as well as intra-set and cross-set testing scenarios. The dataset used is shown in this table. Overall, our RFGuess achieves a cracking success rate comparable to deep learning-based methods and outperforms other statistical-based guessing methods. However, RFGuess suffers from slow password generation speed and high memory consumption. This makes RFGuess particularly suitable for online password guessing attacks, where the number of guesses allowed is small. Next, I will introduce our targeted guessing model, RFGuess PII. In targeted guessing scenarios, we first need to solve the disambiguation problem of PII matching. For example, the password WANG1231980 has 3 possible representations. Which one should we choose? To address this issue, we propose a PII matching algorithm based on the principle of minimum information entropy. The core idea is to systematically enumerating all potential representations of passwords, sorting them by frequency, and identifying the representation with the highest frequency as the priority representation. This process continues until the frequency of all representations becomes 1. The feature construction method for RFGuess PII is similar to RFGuess. The difference lies in treating a string containing personal information as a PII segment. Each PII segment is represented by a 4-dimensional feature vector. They are PII type, PII behavior serial number, 0 and 0. Here, the last 2 zeros are used to align with the feature of an ordinary character. Here is a toy example. WANG is a PII segment. Moving on to the datasets and the experimental setup for RFGuess PII, we have used 6 password datasets. Similarly, we set up intra-set and cross-set guessing scenarios. Now, let's discuss the experimental results. Overall, our RFGuess PII outperforms existing PII models by 7% to 13% within 1,000 guesses. Next is the RFGuess reuse. It's a targeted password model based on password reuse. It involves 2 main steps. The first step is to count the structure-level operations of password pairs in the training set. And the second step is to predict the segment-level operations using the random forest model. Then we can use PW1 to generate a number of reused passwords. Now, it's the datasets and the experimental setup for RFGuess reuse. We have used 8 datasets containing password pairs. They are obtained through email matching. For example, A right arrow B means that a user's password at service A can be used by an attacker to help attack the same user's account at service B. The experimental results show that our RFGuess reuse is generally comparable to existing SOTA reuse models within 1,000 guesses. Finally, is the general applicability of our password character encoding method. It's applicable to a series of supervised machine learning algorithms that can tackle multi-classification problems, among which boosting methods perform well. Thank you for your listening. Please feel free to ask me if you have any questions.